Hello again. Let's get started. Let A be less than C less than B, and let F be twice differentiable on the interval A comma C, or should I say the open interval A comma C union open interval C comma B, and continuous on the overall open interval AB. Guys, keep in mind, this right here is really just the open interval AB with the point C deleted out of it. Okay, so we are defined and we're continuous at C, but we're not necessarily differentiable at C, let alone twice differentiable at C. We don't even know if we're once differentiable at C. We know we're continuous and defined at C, but we don't know anything else about our behavior at C. We can't make any further promises. Let P be a positive real number tiny enough such that C minus P comma C plus P is a subset of the open interval AB. If F double prime of C minus Q, or should I say if F double prime of C minus Q, that's the second derivative of F, evaluated at C minus Q, recall. So if F double prime of C minus Q and F double prime of C plus Q, neither one equals 0, and have opposite signs for any Q between 0 and P, that just ensures that F is defined, at these points, then C is said to be an inflection point of F. The sign of F double prime in other words, what we're saying informally is the sign of F double prime to the immediate right of x equals C is the opposite of the sign of F double prime to the immediate left. So if the sign of F double prime to the immediate right of x equals C is positive, say, then the sign to the immediate left will be negative and vice versa. So it's opposite. Now, guys, what F double prime evaluated at C itself? One or two things is going to happen. Either F double prime of C will equal 0, or else F double prime of C will be undefined. It won't exist at all. So F double prime of C can't equal anything but 0. It will either equal 0 or it won't exist at all. It only has those two choices. C is called, in this case, C is said to be an inflection point by definition. So, in other words, an inflection point is a place where C is an inflection point by definition if F double prime changes signs at C. Now, F double prime may equal 0 at C, or it may be undefined at C, but it will change signs at C. If you go to the immediate left of C, you'll be either positive, you'll be either purely positive or negative, and to the immediate right of C, you'll be the polar opposite of what you were to the immediate left. Okay. Now, let's do an example. Let F be a function from the reals to the reals such that F of x equals x cubed. Then F double prime of x equals 6x. Remember F double prime, you differentiate twice. You do the derivative twice. F double prime of x equals 6x, which is certainly greater than 0, and I should say for x on 0 to infinity, for x on the positives, because if x is positive, 6x is certainly positive. And if x, however, and F double prime of x is, which of course again is 6x, is negative if x is negative, and F double prime again is 6x, which is 0 if x itself is 0. So, 0 is where the change happens. And naturally, remember the graph y equals x cubed? It looks like an old man sitting in a chair, or an elderly man, I should say, sitting in a chair. Hence, F is concave up on 0 to infinity. It's concave down on negative infinity to 0, and it has an inflection point at x equals 0. So for y equals x cubed, F double prime changes signs. The graph is smiling to the right of the origin. It's frowning to the left of the origin. So just F double, it's not F prime that changes signs, beware, it's F double prime that changes signs to the right and left of the origin. So the origin is where F double prime changes signs, because that's the inflection point. We're discussing F double prime. We're not really discussing F prime per se. It's more F double prime that we're directly discussing. It's the second derivative. Okay, so F double prime goes from, it's positive on the right of the origin, it's negative on the left of the origin for y equals x cubed. And y equals x cubed, I hate to draw without, I didn't get my ink to go up here in time, but if you could follow my cursor, you go like this, and then you get flat at the origin, and then you go up like this. So you're smiling to the right of the origin, you're frowning to the left of the origin. So yeah, you change concavity. You're concave left to the, you're concave down to the left of the origin. You're concave up to the right of the origin. Okay. Because again, and remember, concave up, the graph is above its tangents. Concave down, the graph is below its tangents. Okay. Anyway, now let f be the standard parabola in this next example. Then f double prime equals 2, which is always a positive number for all real numbers. Hence, f is always concave up. We have no inflection point because if we're always concave up, we never transist from concave up to concave down. There's no chance for us to even have any inflection points because f double prime is always positive 2. And that's kind of no fun. It's easy, but it's no fun because we don't have any inflection points to speak of. Now let f be a function from the reals to the reals such that f of x equals x squared for x non-negative, if x is either 0 or positive, and f of x equals negative x squared for x negative. Then f double prime equals negative 2 for x to the immediate left of the origin, or x equals 0, I should say. And f double prime, now keep in mind f double prime equals positive 2 for x to the immediate right of x equals 0. Hence, x equals 0 is an inflection point of f. Note, however, that f double prime does not exist. So f double prime of 0 does not exist. Guys, the reason is if you were to do the first derivative of this, you would get the absolute value. You would get the f prime function would be literally the absolute value function. Remember, the absolute value function is continuous at the origin, but it is not differentiable at the origin. So you can only do, you can do the first derivative of this guy at the origin. F prime of 0 will exist at the origin, but f double prime of 0 will not exist at the origin. Again, just ordinary f prime of 0 does exist at the origin, but f double prime of 0 does not exist at the origin. Indeed, f prime of 0 equals 0, but f double prime of 0 is undefined. Because we get the absolute value. If you try to go what it is, if you were to draw the graph of f prime, you would get the absolute value function. So you remember in previous videos we discussed, sometimes you can do the first derivative, but you can't do the second derivative at a particular point. And indeed, that's what happens here. Remember, at inflection points, I didn't promise you that f double prime would exist at that inflection point. I promised you that it would equal 0 if it did exist there, but I didn't promise you that it would exist there in the first place. And this one doesn't exist there at all. Okay. So again, an inflection point is where you either go from concave up to concave down, or from concave down to concave up. And 0 is an inflection point. It's just it just happens to be one where f double prime, or x equals 0 is an inflection point. It just, again, inflection points, x equals c is an inflection point. It's a domain value where f goes from concave up to concave down, or else the original f function goes from concave down to concave up. Okay, it's the original, f itself is what we define to be concave, either concave down or concave up. Well, really, f itself, I need to say f is either concave down or concave up. It doesn't make sense to say that f is concave. F is either concave up or f is concave down. And again, whether it lies above or below its tangents, But anyway, moving on. Let f be the original function, be a function from the reals to the reals. And again, now guys, the inflection point is a domain value x equals c, where f double prime, changes signs, where we go from concave up to concave down. Now, if you're concave up, f double prime will be positive, and if you're concave down, f double prime will be negative. And did I state that earlier? I hope I did. If I didn't, I'm going to feel really, really embarrassed. Okay, yeah, I did. Okay, I hope I did. I think I did. Yeah, on the previous video, if I did on the previous video, I'm good. But lest there be any mistake, yeah. Recall that if f double prime is positive, yeah, I did, I'm good. Okay, so I've covered my bases, I'm good. So a positive f double prime means we're concave up, we're above our tangent lines, that's good. Okay, let's move on. Okay, I covered my bases. All right. But again, we're just undefined at this inflection point. An inflection point is a point x equals c, where we go from concave up to concave down, or vice versa. F double prime goes from negative to positive, or else f double prime goes from positive to negative. So f double prime either goes from negative to positive or positive to negative, aka f itself goes from concave up to concave down, or vice versa. Finally, I just had to find my vocabulary. I couldn't find my silver tongue there, so to speak. I got tongue-tied, and I'm sorry about that, guys. I just, sorry. But anyway, moving on. Let f be a function from the reals to the reals such that f of x equals x. Then f double prime of x equals 0 for all x in the reals. Now, you're tempted to say that every real number would be an inflection point. Every domain value would be an inflection point. That's not true. Nobody is. We have no inflection points. Hence, f has none. You're like, well, Jason, why not? Because remember, f double prime has to go from positive to negative, but that can't happen if f double prime is 0 everywhere. We have no inflection points. It's great that f double prime is 0. Take x equals 5, for example. It's great that f double prime of 5 equals 0. But to the immediate left and right of 5, we've got 0 behavior there too. That's not so great. We don't change sign. F double prime doesn't change signs. So we can't call 5 an inflection point. It's not. Okay. Let's move on. The first derivative test versus the second derivative test. The first derivative test, let f be a function from the open interval ab into R such that f prime of c equals 0. F double prime, back up. Let f be a function from the open interval ab into R such that f prime of c equals 0. F prime is negative to the and such that f prime is negative to the immediate left of x equals c, and such that f prime is positive to the immediate right of x equals c. Then f has a local minimum at x equals c. Now everything I said here is correct, but my wording is a little funky. Let me put and such that, and let me put a comma, and let me put and such that, just to make this clearer. I didn't say anything wrong, I just didn't say it as pristinely as I could have. And such that f prime is... There we go. So let f be a function from the open interval ab into R such that f prime of c is 0, so we're flat at c, and such that f prime is negative, so we have a negative slope to the immediate left. The original function f has a negative slope to the immediate left of x equals c, aka f prime is negative. That means f itself has a negative slope, remember. So such that f prime is negative to the immediate left of x equals c, and such that f prime is positive to the immediate right of x equals c. So to the immediate right, the original function f has a positive slope. Then the original function f has a local minimum at x equals c. Let f be a function from ab to r such that f prime is 0, f prime is positive to the immediate left of x equals c, and such that f prime is negative to the immediate right of x equals c. Then the original function f has a local max at x equals c, and I kind of need to put the same trimmings on this guy I put on this guy. I might do that later, but let me move on for now. You get the idea. Guys, for this one, think about just our old buddy, the classic parabola y equals x squared. To the immediate, and think about the origin. At the origin, we have a local minimum. To the immediate left of the origin, our tangent lines have negative slope. And to the immediate right of the origin, our tangent lines have positive slope. For our buddy, I'm talking about, again, our old buddy, the classic parabola. And our minimum is, naturally it's the origin. So, and again, to the immediate left of the origin, our slope is negative. To the immediate right of the origin, our slope is positive. And again, c in this case would be 0. Now, you can pick other examples where the c values are not 0, but let's keep life easy, okay? Now, and in a similar vein, if you want to do the maximum, just use our old buddy y equals negative x squared, the upside down version of the classic parabola. Now this time we have positive slope to the immediate left and negative slope to the immediate right. It's the opposite scenario. Okay, but you get the idea. Okay. Now, if f prime of c equals 0 and f prime has the same sign on both the immediate sides, or to both the immediate left and immediate right of x equals c, then f has neither a local min then f does not have a local min or a local max at that point. Then in other words, f does not have a local min or local max at x equals c. Let me see. Here, keep in mind, guys, back in these definitions, we say that f has a local min at x equals c. X equals c is the location of the min, or the location of the max, depending on which one you're dealing with. F of c would be the min or the max. C itself would be the location of that min or max. C is the domain value. It's the location. F of c is the actual value. Okay. Now, and the same thing, now down here, this one is weird. Now, c is, again, the location. Now, what if we have the same, if to the immediate left and immediate right, if we're positive both to the immediate left and immediate right, or else if we're negative both to the immediate left and immediate right, then we have, then at x equals c, f of c is neither a local min nor is it a local max. X equals c is not the location of a local min, nor is it the location of a local max. It's neither. Okay. Well, and I need to be careful, and I need to put at x equals c. Now, it may have others somewhere else. I don't promise that it doesn't have anybody anywhere else. It just doesn't have one at x equals c. And I need to say that in the editing. It's just not going to be any good local, we're just not going to have a local min or max at x equals c. Now, there may be another point where we might, we don't know. But anyway. Example, consider the function from the reals to the reals such that f of x equals this polynomial right here. We get f prime of x equals 6x minus 4. Just doing the first derivative, power rule. Now, if we want to get a local, now this is a right side. Keep in mind, guys, by algebra 2, the 3 in front here is positive. The lead coefficient is positive. This is going to be a right side up parabola by algebra 2. So we're going to have a minimum. We're not going to have a maximum. Hence, f prime of x equals 0. Now we get f prime of x equals 6x minus 4, but we know that 6x minus 4 equals 0 if and only if x equals 2/3. So 2/3 is the location of our local minimum, which also happens to be our absolute minimum, by the way. And guys, I'm going to have to take this up on the next video because I'm out of time. I hate about it. I'm so sorry. I'll see you on the next video. Bye. Sorry about that. Bye-bye.